two things. Can everyone hear me?
Yes, all good.
Great. And can you see me and are my slides, they look the right way to you? They're not backwards or something?
It's okay, right? It's fine.
Okay.
Perfect.
Great.
All right.
Okay. Well, then I'll get into it. So thank you for having me. I'm excited to tell you all about, how to look at these problems in this space of human AI systems, particularly for NLP, which is my focus area. One tiny change, as you can see up there, I've scratched out databases and written dialogue. The reason for that is that because of the ACL anonymity policy, the piece of that talk I was going to use there, it doesn't work. So I'm giving you something else instead, but still in this space that I hope you'll really find interesting. So before I dive into actually describing this work and telling you my thoughts on how to approach these types of problems, I want to briefly tell you who I am. So, I really started with a pure NLP background. So at the University of Sydney doing my undergrad in syntactic parsing. I then went to Berkeley where I worked again on syntactic parsing, but also starting to broaden out to other topics, but really within NLP. And then it was at my postdoc at Michigan that I started to really think about this human element and start to think about how we build systems that have humans as well as AI models and what those interactions mean. I think a lot of AI people really just think about the AI problem and say, okay, once I have a system that's getting 95% accuracy or whatever measure, I'll hand it over to an engineer and they'll build a system. And this is when I really started to change my perspective and say, no, if we want to build these effective systems, we need to think about the people and the machine from day one in our research. I then was briefly a visiting scholar at Harvard, really getting into HCI with NLP, and now I'm at Sydney. And so you'll hear a little bit about the types of things I'm interested in this talk. Broadly, I would say it's about people, AI, and language all put together. Now, when I talk about NLP, in my mind, it's a field that crosses over into many other fields. So I sort of think of it as having all these different dimensions. Obviously, there's a linguistics aspect. There's an aspect of data science and computer science and machine learning, but also into HCI and software engineering. So all of these pieces you'll see will come together in each of these sections. So first, I want to talk about human AI collaborative systems for diverse dialogue data. And to explain why I'm interested in this, first, I want to talk about sort of the classical dialogue system. And I will note, we have things like ChatGPT today that can be really impressive, but they're not deployed into your phone as the app when you talk to your bank or when you try to use, some other smart assistant. And the reason for that is we often, as people building these applied systems, really want to have tight control. And I think this is going to be true for a little while as we continue to want to maintain control over these systems. So what do they look like today? Typically, you have a question like this one, where I'm trying to find a cafe nearby. That goes into two components. One is all about intent detection. So working out broadly what question I'm asking. And so you could think of that as looking up an API, and there's a whole bunch you can choose from. It's a classification problem. The other side is extracting key information from the question. So here, I'm specifically looking for this cafe, not any cafe, but one in particular. And so I want to find that cafe and look it up and get instructions of how to reach it. Now, those two yellow boxes are both powered by data. And the question I'm interested in this section is, where does that data come from? It doesn't just fall off trees. You can't just go to Reddit or Twitter or X or find it. We typically have to create these data sets with specific goals in mind. You have building a system, you have a client, or you have your own company, and you have a certain set of APIs that you want users to be able to query. You have a certain space of arguments they can provide. So you want to really meet those needs. So how do we get this data? Well, the classic thing you do is you talk to the crowd. And that can take a few different forms, but the standard approach is some sort of question like this one, where you go and use paid crowdsourcing services, Mechanical Turk, Prolific, Upwork, all these different services that exist. And you ask people to produce examples of the question you're interested in. And so the problem with this approach is that it may not give you diverse enough data. And to see what I mean by that, I'm going to tell you about this first paper. So here's an example. You get this question back. First, I want to tell you about this paper we had in 2017. So we're taking you way back to tell you the arc of this story. And here with this analysis paper, just to say, what do people write in these tasks? And to explain that, I want you to think about the range of ways you could express a specific intent. So here, for example, I'm starting a timer. Here's one way to say it. Here's another way to say it, and more and more. So we have all these different ways of expressing this intent. And I've laid them out on the slide so that the ones that are very similar are close together. So you can see that's really small. And the ones that are further apart are a little bit further, more different in terms of the content of the text. Now, this is some vector space. It's a 2D projection of some vast vector space. So if you want to think about it that way, you can think of each of these points as one in some semantic space where they all correspond to the same meaning. So now I'll take the messages away, and let's just think about what this space looks like. And it's going to be a pile of dots. There are lots of ways to express. And remember, this is just one intent starting this specific timer. So there are lots of ways to do it. And here's the question. If you go out to create a data set, and you're doing that so you can train a system, which of these little gray dots are you going to get back? And when you ask the crowd, what are they going to do? So they might give you this set of yellow dots, or they might give you this set that looks like this, or a set, that looks like this. And our question was, can we do experiments to probe which of these you're getting back, how diverse the data you're getting is, and can we make modifications to push people one way or another to give us more diverse data? So here's the setup. We have a standard task. You're asking people to paraphrase or reword sentences. And we're telling them, here's the thing we want you to do. Here's some examples. We're going to have some incentives. We're going to choose what they're shown as the thing to paraphrase. And then we'll collect their responses. We might collect one, we might collect two, and so on. And we varied all these aspects in a controlled way to see what the impact was, both on diversity and on grammaticality and correctness. So obviously people can make mistakes, so we want to really understand how accurate they are. And here's what we found. So first, the examples you show people really matter a lot. So, sorry, I'm just going to make one modification to my screen here. There we go. Hold on. Just adjusting things so I can see a bit better. Okay, so if you change the examples, then people give you more diverse or less diverse examples. And this is statistically significant. And so by having diverse examples, you get people to have more diverse responses. So next, considering the prompt. If we show 5 people the same prompt, then we get kind of similar responses. If we show them 5 different prompts, we get more diversity in their responses. And the third is if you think about the domain that we're showing people, that matters a lot as well. So some domains are naturally more diverse than others. So given these observations, we really need to amend this picture and say, if you have this black dot that is your initial prompt that you're showing someone, what you get back is these yellow dots. So most of them are nearby, but a few of them are way far away in the space, but it's mostly nearby. So this was our observation, and that then motivated a series of papers exploring how to improve this diversity. Because in practice, when you deploy a product, you're going to have the issue that you will see this whole space. Your users are going to give you all these gray dots, right? They're going to say things in all sorts of crazy ways, and you want to be robust to all those ways of expressing things. So our first idea, and this is in this follow-up work a few years later, was to say, let's imagine we can jump to the other side of the space, way over there, and give that as a prompt. then what will people do? Or let's consider these ones that are far away. They're going to be more diverse. And sometimes the ones that are outliers or unusual are going to be errors. So these outlier examples that we're collecting could be really useful. Either they're an error or they're really interesting. And that's a more general observation that I think is interesting to reflect on. The error case has really been studied before. So there's a long line of work saying let's use outlier detection as a way to find errors in our data. But what about these interesting examples? How can we use them? And our idea is let's take one of them, make that the prompt for the next stage, and do another round of data collection. And now we've jumped across the space and we're collecting a different sample of the space for our models. And so if you combine the red and the yellow dots, you're sort of covering the space better. And so this is the intuition for the approach. We're using outliers to drive the selection of prompts so that we can get more diverse data. How do we actually implement that? Well, first I'm going to tell you our baseline approach. It's pretty simple. We have some prompt. We get some workers and we say, can you write paraphrases for us? We get a bunch of paraphrases. Then we check those and keep the data that is correct. Okay, so much for the baseline. The outlier-based approach is going to be very similar. We're going to start with a prompt. We're going to collect fewer examples at first. And what we're going to do is we're going to rank them. And you could do this in any way, and we're ranking them based on similarity. So I have some details in this box of the particular model we used in this paper, but really you can choose your favorite similarity metric. You can do whatever you want to decide that ranking. And then the ones that are most similar, we're going to put straight in our data, because we're going to say, look, they're really similar semantically according to our model, so they're probably correct. There's no need to check them. For the ones that are less similar, we're going to check those. If they're correct, we'll put them in the data. And the ones that are most unusual, these outliers, are going to go back to drive the next round of prompting. And so that's how we get to this outlier-driven process. And we'll go through the process a few times to collect progressively more diverse data. So these are the two approaches. How well does this do? And I'm going to consider a few different metrics here. So first, what we're going to do is train models on data from these two sources, either the baseline approach or the outlier approach, and then we're going to evaluate on the two as well. Now, this is a pretty easy task, the way we've set it up, I will say. So on the baseline data, with baseline data, you can get it almost perfect. But that model evaluated on outlier-based data, so more diverse data, drops in a huge way. There's almost 20% drop, so things are wrong a fifth of the time. You're going from a useful product to one that users won't tolerate. And so this is showing us that our data collection process is giving us a biased perspective of the performance of our system. And in particular, if we relied on data collected in this baseline approach, we might think we've got a great system, but then when we deploy it, our users will have all sorts of creative ways of phrasing things, and our system's going to fall over. So that's the bad news. So we're finding out that models trained on the baseline data are not robust to the long tail of ways people express things. Okay, what about if we train on data collected with the outlier approach? Well, it does well in both scenarios. So it continues to do very well in the baseline case, and it recovers that performance in the outlier case. So this is good news. Collecting more diverse data just gives you a more robust model. Okay. So, however, when I describe that approach, I mentioned things could be errors or they could be super interesting. Let's think about that error case, which is this one over here. So that the box I had. Now here was our process. The way errors are interesting here is that we have this branching point where the really similar ones don't get checked, they go straight in the data, and the ones that are quite different have to get checked. And there's a question of, well, what is the balance there? You have a cost saving because you don't need to check some, but you have a risk that you introduce errors. So we were very conservative and we said, let's set this threshold so that we get no errors in our final output. And in this setting, for those two, we were able to actually have 60% of the cases, yes, going through checking, but still reducing it almost by half, reducing the amount of checking, which is a significant saving. Okay, so that's one way to increase diversity. Here's another. So this is a separate paper a year later. Now what we're going to do is say, we have this prompt. What if we could tell people, just don't give us anything in this little box I've drawn over here. So just please leave things out of that. Give us stuff that's still a paraphrase, but not too close. You get these blue dots, which is nice. It's a different type of variation. Now, that's the intuition for this approach. But how do you actually tell people to do this is the trick. Because I can't think in hypercubes. I can't have you tell me, here's a 400-dimensional box. Don't give me a paraphrase inside that. So how do you express this in a way that people can actually interpret? And the idea we had was to draw on something from Louis von Ahn, looking at the ESP game. So briefly, the relevant parts of this for this talk are that they would show people a prompt, which is an image in this case, and they would play as two people playing together, and they would have to say what's in the image. And so in this case, they might say, building. And then they would say, okay, you have to come up with more labels, but you can't use one of the existing labels. So given that that becomes a taboo item, they might then say tree or something else. And they'd keep going, adding more labels for this image. And this was a cool way to label images. Lots of people played it. It was quite successful. And so this is one way to tell people to give them more diverse answers. By putting things on the taboo list, they push people to be more creative. So can we do this for text? Well, here's a sentence. What is the capital of Florida? If I take that, someone gives me a paraphrase. In this case, what city is the state capital of Florida? Which is fine, but not that exciting. If I now make that a taboo item, then they can give me something like this, which is very similar. So we're not really getting anything that diverse. And the reason is because language is so diverse that small changes can retain correctness and meaning and grammaticality and so on, and not give us interesting diversity. So clearly directly applying that prior approach isn't going to work. What can we do instead? Well, our idea was, let's make a single word taboo and say you can't use this word in your answer. If we make that word Florida, and then we get variations like this, where people talk about the Sunshine State or FL, so they're using the acronym. If we say you can't use the word, sorry, and this is blowing off my screen, capital, then we get these kinds of variations. So again, it's other ways of phrasing capital. And if we say what, then we get quite different phrasings of the entire question. So this is really cool. And I should note, these are all actual examples written by actual workers in our data set. And the two things I want to point out. One, we're getting interesting variation. So, we're getting unusual cases we might not have otherwise. And two, it's a really targeted type of variation. So you look at the Florida case, and most of the sentences, they leave exactly the same, and they just change the part that they're not allowed to reuse the word Florida. And so we're guiding them to be creative in particular ways, which is pretty cool. Now, you don't need to have it be just a single word. So let's take this request for a flight, and we can make a whole bunch of words be taboo items. If you do that, people start to become maybe too creative. And again, I've changed the city names, but otherwise these are real examples from the data set. So one thing they said was, find an airline schedule from Sydney to Luxembourg. Okay, that's reasonable for this. Show me plane rides from Sydney to Luxembourg. Probably not something your user will say. This is getting a little bit unusual, so maybe it's too creative. And we also got, how may I traverse through the air from Sydney to Luxembourg? So this is clearly weird. We've pushed them too far. You're very unlikely to get that from any user ever. So maybe 6 words is too much. But you can tune this. You can choose the number of taboo words to suit your application. So this is the idea, this is the approach. But how do we do it? And where do we combine human and machine effort in this? So we're going to have the same baseline as before, the same one I described in the previous section. But for our system, we're going to have it run a little bit differently. We provide the prompt. Again, we collect a small number of samples. We then check them. So the top is exactly the same as the baseline. But then in our next round, we're going to select these taboo items. And in this approach, we took a really simple model. So we said, let's just train an SVM with bag of words features, really simple model, right, to do the task. And the nice thing about this is we can directly inspect the model and say, okay, what are the features that are very predictive of certain classes? And we're going to make them into taboo items. So for the next round, people can't select them. And you can see I've highlighted the words that seem to come up a lot in this case. And this is nice because we are identifying the words that essentially our model has already learned about, that are already learned as being a nice correlation with our prediction. And so we're guiding people to give us other phrases that we may not know, but would be indicative as well. And so this is the approach. And we're going to evaluate it in the same way, where we train models using data from the different approaches, and then evaluate on data from the different approaches. Now, we also changed to BERT, and of course you could change to the latest and greatest models, and I think you'd find the same results. So first, every approach does well on the baseline data. It's just really easy to process the baseline setting. And again, the training on baseline data does poorly on these diverse data sets. So it's not quite as bad as before, BERT improved results a little bit, but it's really not robust to those other settings. So that's the first observation. Here are the results for the other models. And there's something interesting going on. So I'm going to zoom in on those. The outlier-based approach does well on the outlier data, but less well on the taboo data. And it's vice versa for the taboo-based data. So you can see from this that we're getting at different types of diversity. The different models are learning from their data, but they don't generalize to the other ones, which is reflective of that picture or the sort of cartoon I've been drawing across these slides with the dots. But it still means, okay, neither one sort of solves the problem. You really need both. So they're getting at different types of diversity. This leads to the idea, why not combine them? So now in purple, I have a model that's trained on a combination of data. And I should note, in every case, the amount of training data is the same. So we just use samples from the different data sets. And so what this shows us is that by combining these sources, you can get a model that does well everywhere. Now, this also raises a potential issue, which is that we've identified two sources of diversity here. There are probably more. There are probably other approaches out there. And so if you can find other ways in which to create more diverse data, that could continue to improve your performance overall and increase the robustness of your system. So here's the final picture. We first had this observation that there's this big priming effect. The data we show people, the examples we show people, they really shape what they do in these tasks. Using this outlier-based approach, we can get diversity, and using the taboo-based approach, we can also get diversity, and putting them together, we can get better results overall. And in each of those cases, it was a combination of human effort in terms of crowd workers, and also some sort of model. So there was either the similarity calculations in the outlier-based data approach, or for the taboo-based approach, there was a model to identify the terms that we were going to use. And by combining those efforts, we get this overall better result. So I'm going to pause on this slide. This might be a good point if there are any questions on this section. I'm also happy to wait to the end to take questions, but if anyone wants to jump in now, please do. Okay, and hearing nothing, I will forge on, but I'll be glad to take questions about this section as well at the end. So now I'm going to change gears a little bit and think about some, oh, there was a question?
Yes.
So I have a question. So
because this is like 2020, and we try out again now with things like ChatGPT and say, and if try to see crowdsourcing easier, try to see easier and you get similar results.
So the signal's breaking up a lot. I heard ChatGPT and crowdsourcing, but I didn't get enough to really know the question. I don't know if there's a different microphone or something you could use.
Can I try again? Thank you. Can we hear me now?
Yep, I think that's a bit better.
Okay, so my question is that now this our language model, the ChatGPT, this was back 2020. So did you try out to mix it ROS with LLMs instead of human and see guess results from without a human at all?
Yeah, so I'm going to paraphrase. Again, the connection is still not great. Hopefully you've been hearing me well. So my understanding of the question is, with ChatGPT, could you essentially take the human out of the whole equation and have ChatGPT or some other large language model be generating these things? Which I think is, a great point. And actually I was discussing just the other day with some of these collaborators from this work about that possibility. I think you could try that. And that would help in some ways. It would work in some ways. I think it would struggle to get quite the diversity we see here. And the reason is, ChatGPT does a great job if you, in terms of producing coherent, great responses to things. But if you turn that temperature up to try to get greater diversity, then it'll start to hallucinate or go off the rails. So that's just the nature of it, right? You're trading off diversity and accuracy. So the question is, could you have a model that gives us the diversity we're seeing here without bringing in too many errors? And that's unclear to me. I think it would be really interesting to try. I also think there's scope to incorporate ChatGPT or a similar model, some large language model, in various ways in this process. Obviously, the valuation of paraphrases, are they equivalent? That's one thing you could use. Also, you could imagine generating some that are checked by people. So there are lots of variations here, but I think there's a space for exploration. And these techniques could still apply, obviously, in conjunction with it. So lots to explore. I think there's still a role for people, though. Hopefully that answers the question.
Yeah, thanks.
Great. Okay. Cool. Well, I will go to the next step, which, as I said, I'm going to change gears a little bit and talk about ethics. And specifically, I'm focusing here on paid crowdsourcing. So Mechanical Turk and those other services. Oh, can you hear me?
There is one more question.
Oh, sorry.
Do you hear me?
Yes, I can hear you.
Okay, thank you. So this is a question related to this part of the mentioned that that we pick up the long-tail distribution is that ones are either outliers or the data point that would be incorporated just in your data set. So you mentioned that there is all kinds of validation, semantic validation of the data points to incorporate that information in the data. Can you say some words about this? How do you perform such a semantic validation?
So again, the connection's really not good. It's sort of I don't know what it is about the room. It sounds like you're far away from the microphone or something, the connection's bad. But I did hear validation and saying more about the validation process for confirming the data. So apologies, that's not quite it. In terms of the validation process, we manually check all the data because in this case, we really want to be confident that it's exactly right. So there are two aspects to validation. So for the experiments, we checked all the data. So we had a gold standard label of, is this accurate or not? And that allowed us to do the comparison so we could know, the metrics we're calculating, whether they're accurate. Separately, there's the question in the workflows I described of do you get people to check or not? And obviously we can simulate that once we have the gold standard information and make that the threshold I described. But yeah, we were manually checking. That checking process, interestingly, is typically much easier and faster than the creation process. I know of companies where the creation process is crowdsourced, but the checking is done internally because you can rapidly read through and say yes or no, but writing is quite slow. Or you could imagine having more experienced crowd workers who are trusted to know and be able to really give you an effective label. So yeah, that was something we did entirely ourselves. And one thing I don't do here is estimating exact costs. I mean, I do in the paper, we have details on how much we paid the workers to write these things and how much time they took. But you would have to consider the time for that checking process as well. Yeah. And you need that obviously for ChatGPT too.
Yeah, we're good. You can continue.
Cool. Okay. I'm going to make one little change. Oops. This is the wrong thing. So just shifting my windows around so I can see everything a bit better. Actually, apologies. I haven't used WebEx before for talks, so still figuring out the right workflow. Okay. So now talking about ethical issues in human AI systems and what I'm going to call qualification labor. If you don't know that term, that's because I made it up. So you're about to learn what it means. Here is the context for this. Here we have a bunch of people. They are a crowd, and we're going to be hiring some of them to do our tasks for us. And when you do this, you can set minimum requirements for participants. So some common qualifications, which will be numbers assigned to each person based on their work on the platform previously. So here are two common numbers. So the top one that I've put in green in some cases now is the number of tasks they've successfully completed. And I might set that to say, you need to have done 5,000 tasks. If I do that, I'm going to get these 3 green people. I'm not going to get the other 3 because they haven't done enough tasks for me. People use this frequently because it means you're getting more experienced workers who have done more of these micro tasks and so might have a better sense of how to do them, what the process is, be faster. They might just be more, believed to be more reliable. Another measure is this percentage, and that is what percentage of tasks you've done have been accepted. And so you can get a sense of how often their work is rejected. And maybe you say you only want people with 99% or above, and then you get these blue people. And obviously you can combine qualification requirements as well. In this case, if we had both of these, we would only get this one blue-green person who has done over 5,000 tasks and has an acceptance percentage of over 99%. So these are qualifications. They're widely used, very standard in lots of tasks, and a really critical tool. These are 2 examples. These are probably the 2 most widely used ones. There are a whole range of other ones with varying levels of interest. Obviously, for certain tasks, some are very important, like experience with particular languages, but these are the most widely used. So what are the conventions for these qualifications? And I did a bit of digging in a range of sources to say, what is the threshold specifically for this number of tasks completed? And so I looked directly at Amazon itself. I looked at blogs, papers, and courses and other sources and considered a range of numbers. And here's what I found. So each of the numbers in this table gives a threshold. And the green indicates what I found. So Amazon in their blog, or at least I don't know if it's still live now, but they used to recommend 5 or 10,000. That was the number they gave. In other blogs of people just discussing how to do crowd work effectively, how to do all this sort of thing, some people say as low as 1,000, but that's the threshold. Papers do go as low as 100, but that 100 is typically either for surveys or it's because there's another setting, that percentage, which only kicks in for people who have over 100 tasks. So sort of to make that actually be effective. So this is sort of what's talked about. The other source I looked at is workers themselves, and they are relatively active online. You can find them talking on Reddit and other forums and things, sharing their experiences. And here's one comment I saw, for your first 1,000 hits, which are these little micro tasks, you may want to concentrate on approval milestones rather than money. Most of the better paying requesters require 1,000, 5,000, 10,000 plus approved hits. So this person is really saying, you have to just do 1,000 where it's just about hitting 1,000. And the interesting thing about this is it means if you are one of those better paying requesters, which hopefully you are if you're doing research in this space or development, if you have this requirement that they have to have done 1,000 previous tasks, you're essentially saying, go work for someone else who pays badly, and then you can come to me. And so you could have some ethical concerns about that. And specifically, I don't have it on the number on the slide, but it's in the paper, if you look at what people say about how long it takes to hit these milestones, reaching 5,000 tasks, which is one very common threshold, could take about 2 months of full-time work on these platforms. So that's a lot of time spent working either on poorly paid tasks, or they're tasks that experienced people aren't willing to do. So maybe moderation tasks with objectionable content or other things that are just undesirable, and so they reduce these qualifications. And so again, you're telling people, go work on those tasks that are unpleasant to earn the right to work on my task. So this issue, what can you do about it? And should you be setting these thresholds at these levels? So I considered 2 tasks. So first, a form of co-reference, where they're going through and selecting which of these entities these noun phrase spans correspond to, and a sentiment task. And the sentiment one is a direct copy of the Stanford Sentiment Tree Bank's task they used to build it. The co-reference one is a new interface that I was working on for a separate project, and is probably something most workers have never seen before. So the idea here was, let's get 2 different tasks and really see how they do in these 2 very different settings. Now, the results I'm going to show you, I set up this experiment in a couple of ways. So for co-reference and sentiment, I'm going to show you 2 graphs. On the x-axis here is the percentage of hits required in terms of approval. So you can tell within those buckets, that's what experience those people have. And on the vertical axis, it's the number of hits that have accepted. So these are these 2 qualification requirements, and I'm doing all combinations of them. And it's a heat map. So darker colors are going to mean more workers did a good job. And in this case, for each task, I had a threshold of accuracy to say, okay, you did a good enough job. And light means they did a poor job. Here are the results for co-reference. And we see that indeed, these qualifications do seem to work. It does seem like the percentage accepted is actually a much more important signal than the number of hits accepted one. But 5,000 also seems like an overestimate of what's required. You can go down to like 2,000 or so and still get workers who are doing a really good job. Interestingly, for sentiment, there is this pattern where the least experienced workers and the most experienced ones did the best. And there's kind of this trough in the middle. And my takeaway from this is really you need to experiment for your task with these different thresholds. And ideally, switch away from paying workers purely based on these thresholds, and instead have sort of a 2-phase recruitment process. So this is this idea where you have a small task that you have very open, allow lots of workers to participate in, and use that then to create your own qualification for them to do future work with you. And that way you set the barrier to entry very low, but you also don't spend a lot of money on people who are spamming or don't understand or doing tasks in a way that is unhelpful. So the takeaways here, and this is intentionally a brief section before we dive into the next one, which is a big change of gears, is really for any qualification you use, consider the indirect impacts. Because everything I've been describing here, you're paying well, you're doing the right thing. It's the indirect implications of the qualification you require. Tune these thresholds, and really use the minimal qualifications to get workers who will do a good job on your task. Okay, so now I'm conscious of the time. I'm going to dive into AI for diplomacy. And this is a complete shift of gears. I've been talking all about paid crowdsourcing and creating data. This is about games and human AI collaboration in a totally different way. If you're not familiar with the game, it's a fascinating board game played by 7 players on a map that's sort of approximate Europe 1901. And there's 7 of you, each one playing as a different power at that point. And the goal is to conquer Europe. So the thing that makes this game really interesting is that it doesn't have turns in the way most games do. Instead, all players simultaneously in private write down a little sheet of paper what your units are going to do on that turn, what your pieces on the board. And then we bring all of those together, reveal them simultaneously, and work out what happens on the board. Now, the reason I say this is super interesting is that it means that if you want to collaborate with someone else, you have to discuss it in language beforehand. In a turn-based game, I can take my turn, do something, then the next person can take their turn, look at what I did, and do the thing that's helpful or unhelpful. But in this game, you can't wait because you're all doing the things simultaneously. So if I want to work together with someone else, we need to agree ahead of time and write down things that are compatible, but I won't know that they've actually done what I asked until it's revealed. So to give you a sense of this, I want to play through one tiny example from a corner of the board. So imagine we're looking at this part of the Mediterranean. There's an Austrian army in Serbia, a Turkish army in Bulgaria, and an Italian fleet in the Ionian Sea. So Austria walks over to you and you're playing as Italy. And Austria says, I'm going to attack Greece. Will you help me? So now you know that Austria is going to make this order over here, send their army south. Then Turkey comes over to you and says, I'm going to attack Greece. Will you help me? So now you know the army in Bulgaria is also moving into Greece. Now the way the game works is if those 2 armies attack the same place, they'll bounce back. Neither army gets control of it. However, if you support one of them with your fleet, that gives them added strength, and then they'll successfully get in. So you have a few options. Here are 3 of them. One is that you can also attack. So you'd have 3 of you all attacking Greece. You could do that. Then you'd all bounce back. The other option is you could help Austria, or you could help Turkey. Now, they don't know what you're going to do until things are revealed. So you could go to Austria and say, yeah, I think we can work together. Let's do it. I'm going to support you. Can you also help me over here on this other thing? Let's work together. Then you turn around and walk over to Turkey and say, hey, Turkey, I just told Austria I was going to help them, but I'm not. I'm actually going to help you. And I've tricked them into thinking this. So let's work together. Then you could go back to Austria and say, hey, Austria, I told Turkey that I was going to lie to you, but actually I was lying to Turkey. Let's work together, and now I've tricked Turkey into doing something. In the meantime, Turkey and Austria could talk and say, hey, Italy is just messing around with us, telling us all sorts of things. Let's both turn against Italy. And so you can see that the language can really get complicated and really get interesting interactions between the different players. As a person who's played this game myself quite a bit in undergrad, it can be a lot of fun. It can also be very tense. But it has these interesting phenomena. So what work has been done on this in terms of AI? Well, one of the earliest systems is one called Diplomat from the mid-90s, which had a whole bunch of ideas in terms of modules and things. I don't believe it's available online. In the early 2000s, the people who just played diplomacy for fun developed their own development environment called the Diplomacy AI Development Environment. So a language for communication and running servers and things. Then at IGCAI in 2018, they had these AI leagues where they would get people to build bots and play against each other. But one thing that was interesting is they found that, there's this quote about here about none of the negotiation algorithms helping. So what this means here is that when they ran the bots with no communication, and when they ran them with the ability to communicate, communicating didn't help, which is really a bad sign, because if you played the game, obviously, as I've just shown you, communication is critical to doing well in this game. And because there are 7 players, everyone is too weak on their own to win. If you can communicate with someone, you can collaborate with them until you decide to stop collaborating with them. So my own work in this space was a NeurIPS paper in 2019, where we considered the version of the game where there's no communication, and we introduced the first neural network model for it. So we have data, we have a neural network, which produces a system called DipNet. Now, the model itself has everything you'd sort of expect from a model developed in 2017 or 2018 or so. It's got LSTMs and graph convolutional networks and some attention mechanisms and all sorts of things. But the details of the network aren't critical. The thing I think that's interesting is looking at the results and then starting to think about what came next. So first we can compare it with people, and we see that it actually does surprisingly well at predicting the moves people make. And these 2 metrics, the difference is in the teacher forcing case, you know about the other moves in the turn when you're choosing your move, or sort of the moves for the previous units. We also find that as you look further along, your ability to predict these support orders gets worse. So it gets harder for later in the order sequence, which makes sense. Playing the game, and I'm going to zoom in here first. Here I have a range of different bots, some of them that are sort of baseline systems developed by other people, and then an RL and SL, supervised learn version of our bot. And in this sort of true skill, which is kind of like an ELO style thing if you're familiar with chess, we can find that we're doing better, although the RL and supervised learning one are pretty similar. If you look at wins, the trend becomes even clearer. We just totally crush a random bot or a greedy bot with a simple heuristic. The dumb bot and Albert start to do slightly better. The one thing to keep in mind is that if you are one player playing against 6 of another bot, you would expect to only win 1/7 of the time typically. So then with the RL case, you can see it's not doing as well, but it's pretty close. We flip it, we see a similar pattern. In the bottom case there, you can see again RL and SL are it's winning 1/7 of the time, but in all the other cases, the other bot never beats us when there are 6 of us all working or playing together. So this was then released online. The diplomacy community was pretty excited to have a bot they could play with that played the game pretty well. It's definitely not at a human level in terms of an expert, but it could definitely beat me as an amateur playing the game. So that was exciting to see it somewhere in the range of human play. Built on top of that, DeepMind and Meta had extensions, and I'm not going to talk about these in too much detail, but essentially these were new ideas in reinforcement learning, ways to sample the space with these different algorithms to effectively have a way to search, because the search space is enormous. You have 34 pieces. There are at least 5 to 10 reasonable moves for each piece. And if you consider the full space, there can be hundreds or thousands of moves for each piece. So it's enormous search space. So in terms of performance, the Meta one, the search bot, it would really do way better than DipNet. So you can see it's winning almost 40% of the time against DipNet. Sorry, I have this backwards. DipNet was, only winning against it. With the DipNet architecture, you only win 40% of the time. They made improvements to the architecture and then introduced their RL algorithms and got these progressive improvements to the point where SearchBot is beating an expert player most of the time. So they got it to the point where an expert player was really being crushed by the AI. So that was very cool. But everything I've been telling you about AI research so far is just with bots. What happened to language? This whole workshop is about human AI connections. It's not just the AI. And this is an exciting space that there's a lot happening right now. So one thing I'm involved in right now is there's a DARPA program called SHADE, where a bunch of us are developing systems to play the game and communicate. and really think about the negotiation aspects, think about how you interact with other players. At the same time, Meta is still moving, and so they've released a system called Cicero that can play the game. And so this takes in the board state, takes in messages so far. It uses those to form an intent about what to do next, develops a set of orders, and then from its plan, so it comes up with a plan for what to do, it then updates, generates messages to send to people. And so you get this system that can both play, but also communicate as well. And so that's really cool. Now, Cicero has been pretty impressive, but it's only in a constrained form of the game again, with really fast turns where you don't have to have as much consistency over long periods. So playing the full game with long turns is still a challenge. But it's a really interesting space for this sort of human-AI interaction and collaboration. And one thing I'm very curious about is to see, once you have these models, how do people interact with them? Do they collaborate with the bot? Do all the people get together and take the bot out immediately? If they start doing that, does it make sense for one player to defect and work with the bot? There are all sorts of interesting dynamics that you get into, and this is an interesting test bed to explore this, as games have been for a long time. So I'm going to stop there just by saying, hopefully one day you'll be able to play with these systems, and hopefully this has got you thinking about this sort of human-AI collaboration and interaction beyond the sort of systems we build today, and thinking about more collaborative ones. So with communication. So thank you. I will stop there. I know it's important also to mention I am recruiting PhD students in the next sort of cycle. So if you know anyone interested in working on these types of questions, I will be putting out a call sometime in October. And so I'd love to have more students coming my way. Thank you very much.